Patterns in nature are visible regularities of form found in the natural world. These patterns recur in different contexts and can sometimes be modeled mathematically. Natural patterns include symmetries, trees, spirals, meanders, waves, foams, tessellations, cracks and stripes. Early Greek philosophers studied pattern, with Plato, Pythagoras and Empedocles attempting to explain order in nature. The modern understanding of visible patterns developed gradually over time. In the 19th century, Belgian physicist Joseph Plato examined soap films, leading him to formulate the concept of a minimal surface. German biologist and artist Ernst Haeckel painted hundreds of marine organisms to emphasize their symmetry. Scottish biologist Darcy Thompson pioneered the study of growth patterns in both plants and animals, showing that simple equations could explain spiral growth. In the 20th century, British mathematician Alan Turing predicted mechanisms of morphogenesis which give rise to patterns of spots and stripes. Hungarian biologist Aristide Linden-Meyer and French-American mathematician Benoit Mandelbrot showed how the mathematics of fractals could create plant growth patterns. Mathematics, physics and chemistry can explain patterns in nature at different levels. Patterns in living things are explained by the biological processes of natural selection and sexual selection. Studies of pattern formation make use of computer models to simulate a wide range of patterns. History. Early Greek philosophers attempted to explain order in nature, anticipating modern concepts. Plato, looking only at his work on natural patterns, argued for the existence of universals. He considered these to consist of ideal forms of which physical objects are never more than imperfect copies. Thus, a flower may be roughly circular, but it is never a perfect mathematical circle. Pythagoras explained patterns in nature like the harmonies of music as arising from number, which he took to be the basic constituent of existence. Empedocles to an extent anticipated Darwin's evolutionary explanation for the structures of organisms. In 1202, Leonardo Fibonacci introduced the Fibonacci number sequence to the Western world with his book Liber ABC. Fibonacci gave an biological example, on the growth in numbers of a theoretical rabbit population. In 1917, Darcy Wentworth Thompson published his book on growth and form. His description of phyllotaxis and the Fibonacci sequence, the mathematical relationships in the spiral growth patterns of plants, is classic. He showed that simple equations could describe all the apparently complex spiral growth patterns of animal horns and mollusk shells. The Belgian physicist Joseph Plato formulated the mathematical problem of the existence of a minimal surface with a given boundary, which is now named after him. He studied soap films intensively, formulating Plato's laws which describe the structures formed by films in foams. The German psychologist Adolf Zeising claimed that the golden ratio was expressed in the arrangement of plant parts, in the skeletons of animals and the branching patterns of their veins and nerves, as well as in the geometry of crystals. Ernst Haeckel painted beautiful illustrations of marine organisms, in particular radiolaria, emphasizing their symmetry to support his faux-Darwinian theories of evolution. The American photographer Wilson Bentley took the first micrograph of a snowflake in 1885. In 1952, Alan Turing, better known for his work on computing and code breaking, wrote The Chemical Basis of Morphogenesis, an analysis of the mechanisms that would be needed to create patterns in living organisms, in the process called morphogenesis. He predicted oscillating chemical reactions, in particular the Belousov-Zhabotinsky reaction. These activator-inhibitor mechanisms can, Turing suggested, generate patterns of stripes and spots in animals, and contribute to the spiral patterns seen in plant phyllotaxis. In 1968, Hungarian theoretical biologist Aristide Linden-Meyer developed the L system, a formal grammar which can be used to model plant growth patterns in the style of fractals. L systems have an alphabet of symbols that can be combined using production rules to build larger strings of symbols, and a mechanism for translating the generated strings into geometric structures. In 1975, after centuries of slow development of the mathematics of patterns by Gottfried Leibniz, Georg Cantor, Helga von Koch, Václav Sierpinski and others, Benoit Mandelbrot wrote her famous paper, How Long is the Coast of Britain? Statistical Self-Similarity and Fractional Dimension, crystallizing mathematical thought into the concept of the fractal. Causes. Living things like orchids, hummingbirds, and the peacock's tail have abstract designs with a beauty of form, pattern and color that artists struggle to match. The beauty that people perceive in nature has causes at different levels, notably in the mathematics that governs what patterns can physically form, and among living things in the effects of natural selection that govern how patterns evolve. Mathematics seeks to discover and explain abstract patterns or regularities of all kinds. Visual patterns in nature find explanations in chaos theory, fractals, logarithmic spirals, topology and other mathematical patterns. For example, L systems form convincing models of different patterns of tree growth. The laws of physics apply the abstractions of mathematics to the real world, often as if it were perfect. For example, a crystal is perfect when it has no structural defects such as dislocations and is fully symmetric. Exact mathematical perfection can only approximate real objects. Visible patterns in nature are governed by physical laws. For example, meanders can be explained using fluid dynamics. In biology, natural selection can cause the development of patterns in living things for several reasons, including camouflage, sexual selection, and different kinds of signaling, including mimicry and cleaning symbiosis. In plants, the shapes, colors, and patterns of flowers like the lily have evolved to optimize insect pollination. European honeybees and other pollinating insects are attracted to flowers by a radial pattern of colors and stripes that serve as nectar guides, that can be seen at a distance, by scent, and by rewards of sugar-rich nectar and edible pollen.